Good evening, everyone, and welcome to the second ADIA Lab seminar of 2025. Tonight, we focus on the energy transition, exploring how technology diffusion can help forecast the future of clean energy. In today's session, we are honored to have two distinguished guests, Professor Doyne Farmer and Professor Mao. And in the first half of the session, it will be led by Professor Doyne Farmer, Director of Complexity Economics program at Oxford Martin School, who will share insights on probabilistic cost forecasting methods for decarbonizing the global energy transition system. Please welcome Professor Farmer on stage. Thank you.
Yeah, and here's my clicker. Okay, so you've all had lots of time to study my first slide here. I always like to start with this slide because really I'm going to talk today about two things. One is about what we can learn about the history of other technology transitions. What does that tell us about the energy transition? And the other one is how can we use agent-based modeling to understand what the energy transition is going to do? How can we understand the economics of the transition and how quickly it will happen and how it will play out? So let's begin with this first slide. I apologize, a few of you have seen this already because I showed it in another presentation yesterday. But this shows the history of energy in the world. And the slide on the right shows the useful energy production. It's in powers of 10, so it's a logarithmic scale, which means that exponential change is a straight line. That's all you have to know. And let's start over here, where in 1880, we have traditional biomass here, this green line, and we have coal, the brown line. So back then, they were equal for dominance in world energy generation. But coal, you can see, took up, and it got a margin of almost a power of 10. That's been widening somewhat. And that was dominant until starting around 1950, or sorry, let's go up to here, 1970, you can see oil and gas, which were climbing at faster exponential rates, reached parity with coal, roughly, though they're still a bit below it. And this slope here is actually if you add all these up, you get the global energy production, which has grown exponentially at about 2% per year for the last 50 years, or maybe more. Okay, this is hydropower. This is nuclear power, which grew very quickly and then flattened out. This is wind energy, which you can see has been growing very fast, lithium-ion batteries, and solar energy, and green hydrogen. So you can see these are all very distinct, except possibly for the early phases of nuclear power, and that they're growing at very rapid rates. Solar energy has been growing at about 30% per year. Now let's go to this side of the picture. In this side of the picture, we see, once again, let's start with coal, which has been going along, bumping up and down, but if you draw a line through this, it's roughly flat. Gas, it might go up a little. Oil, it might go up a little, but basically what you see is that oil and gas and coal cost about what they did in 1880, once you adjust for inflation. Let's just pick a few others out. Here's solar energy in contrast. It's been dropping at 10% per year ever since it was first used commercially in the Vanguard satellite in 1958. It now costs 1/10,000th what it did then. Nuclear power, in contrast, costs about, in the US, about a factor of 3 more. In some other countries, it's roughly flat, but it doesn't go down. And by the way, this pattern of being flat in price is true for everything we mine from the ground. There's 100 minerals in the USGS data set, and they're all roughly flat over a century in cost. So they all go up exponentially in usage, except asbestos, which goes up and then comes down. Okay, so we see solar energy, green hydrogen, lithium-ion batteries, and wind all dropping quite quickly, although wind not quite as fast. So that's the history of the energy landscape, and it's worth bearing in mind with any discussion. Note that if you just extrapolate these solar energy by 2050 or so, it's quite a lot cheaper than energy's ever been. So the question is, will that happen? Given that these have been going as they are, what are the odds that they will flatten out? And so let's try and understand a little bit more about that. But let's maybe first start over here. So, and let's just start in general by talking about the track record for forecasting these issues. Well, let me just say the main forecasting centers that people go to for expert advice, the IPCC and the IEA, have done a terrible job. They've dramatically overestimated costs, dramatically underestimated deployment. Here you see, for example, this is module cost for solar, and you see projections of both the IEA and integrated assessment models, and the slopes are significantly different, always ending up too high when it comes to cost. Similar plot can be made for deployment. If you look inside of integrated assessment models, which are the main tool they use, I'm not going to go into detail about how they work, but they always put in floor costs for solar energy. They say that because otherwise the models tell them just put everything into solar. So they say, oh no, that can't be right. So they put in floor costs. And so these are examples of floor costs that have been placed in those models. And you can see the data has just punched right through all the floor costs, which is not surprising because you rarely see floor costs in data, although I will show you an example where I'm predicting there will be one in a minute. Just to blow things up a little bit, we see the data for solar and wind blown up and on its own with a line put through the middle. And what you can see is that so far there are wiggles in these curves, but roughly speaking, the deployment has been going up exponentially. Okay, why is this not moving? Where's the target I'm pointing at? Okay. Okay, we went backwards. Let's see if we can go to the next one. Yes. Okay. So how do people think about these things? There's something called an S-curve that's traditional model for technology deployment. It's, by the way, also the model for what happens to bacteria growing in a petri dish. And so there's typically some kind of limit. And so adoption starts out slow and then accelerates and then it levels off. And so there's a whole, and here's an example of a functional form. This is called the logistic equation. And you can see the exponential sitting in there. So the way this, if you plot this on log scale, what it looks like actually is a straight line with a growth, and then it levels off. So what you see here on a linear scale is a little bit misleading. Okay, good. Now people have tried to predict solar and wind deployment by fitting S-curves to the data. These are some examples. The purpose of this slide is to show you how silly these attempts have been. So here you see, this is for solar. You see the data, and you see some curves corresponding to things that people fit to the data at various points in time. And these gray lines, what happens is you march along in the data, and every year you imagine you're in that year and you fit to the data so far, fit to the data so far, fit to the data so far. And this is using a naive least squares fitting algorithm. And you get these curves that go all over the place, which isn't surprising because if you go back and look at this curve, you can see that if, well, I should have actually made a plot of it on exponential scale, but it's very sensitive in these early phases. It's very hard to predict when this is going to level off up here. And so that creates a lot of uncertainty. And in fact, you can see also that these fits have been systematically low. These are the published fits. And that turns out to be a generic problem. We've studied this in some depth. if you just do this in the naive way, you tend to get answers that are much too low in the early stages. You only begin to get a reliable answer once you really have the whole S-curve coming in, but then that's too late to be of any use for forecasting what's going on. This is over here for wind. It's a little better. In this case, you actually have some that are too high, though I don't think these were made from simple naive S-curve fits. And in fact, we were sufficiently irritated with this that we had to write a paper basically saying, let's be careful and use proper statistical methods with error bars so we actually know whether, if you're making a forecast, is it any good? And we pointed out just how bad these things were. The figure I showed is a figure that was in this paper. Now, this is a very hard problem, actually. It's hard because, first of all, the data is never as good as you would like. We've spent a lot of time gathering this data. The time series are short. You could see in the picture, we don't, we have 10 or 15 or 20 years or maybe 30 or 40, but it's still short. The growth is inherently a non-stationary process. Things grow and then they reach maturity, so it's not stationary. That makes it difficult. Deviations from exponential growth are small in early stages. We saw that with wind and solar. They fluctuate around, but are those just some noise in the fit, or are those real deviations? What does that even mean here? The noise is what's called heteroscedastic, meaning the noise is small in the beginning, and then the noise gets big, and then the noise gets small again. So you have to take that into account if you want to put error bars on the fits, because that's an important factor. The noise is autocorrelated, meaning if you have an upward deviation at one time step, you tend to have an upward deviation on the next time step. And finally, as I mentioned already, the fitting is strongly downwardly biased because that's the nature of fitting to a sigmoid. Okay. Wait, why did I show this again? I'm not sure. Well, maybe I just wanted to show in this picture that show the deviations from exponential behavior, but let's not worry about that. Now, but let's take a step back. And there are really two hypotheses about what drives technology growth. Just to illustrate, most of the time when people talk about why is solar energy grown so fast in recent history, people say, oh, it's because of China. China stepped in, they've subsidized it, the government's behind it, they're really driving all the growth. Okay, but let's go back and look at this slide. China, when did China step in? I don't know, maybe here, maybe here, somewhere in here, like in the middle of this decade. It was doing almost the same thing before they stepped in. So that's not my explanation for why that's happening. Of course, there was a plateau in the cost in this decade. China helped break through that, but okay, nonetheless, let's go. Come on. All right. It's not working reliably. Okay, all right. Okay. Now, but there's two basic explanations. One is there's some kind of deterministic law that governs the growth process. So if we were talking about bacteria, we would understand that law. Why? Because we know how bacteria reproduce. They go along, they eat for a while, and then they divide. And they do that at a certain rate. It's stochastic, and that you can't predict exactly when a given bacterium is going to divide. But you can actually even write down equations at the level of individual bacteria. They also die after a while. They have a lifespan. And so you can write down an equation that, at least in a good approximation, looks like this. There's some growth rate. There's some constant. That's the rate of reproduction. It's proportional to the current population times the population that will exist when the Petri dish is full minus the population. That equation does a great job of fitting bacterial growth. So you can ask, is there some equation, it might be the logistic equation or some other one, that underlies technology growth? Or is it just one damn thing after another? China, space race, you could write down reasons, the energy Eigenwende in Germany, you can write down something happening in every stage and argue that that's the dominant thing happening. And I will argue they're both right. Well, I'll try and show you that there is a deterministic pattern, but there's noise around that deterministic pattern. And once again, we might need to, is there another way to do this? Yeah.
To reach the clicker.
Okay.
If you want, you can
Well,
near to the
yeah. Where am I shooting? What's the receiver for the clicker?
near the podium.
Near the podium. Okay, that helps. All right. Okay. So, what does this picture show? We took data on 47 different technologies, and we rescaled it so they're all on the same scale. This is a trick physicists love. It's called a collapse plot in physics. So you put things in non-dimensional coordinates. So you put it in time invariant coordinates by adjusting the scale of the the growth parameter, and you assume that they all reach the same plateau and they're all centered in the same spot. And then if the growth were following a perfectly smooth logistic function, you would just see a line, this black line. So that would mean the logistic function described everything perfectly. You can see that's not the case. And you see an interesting pattern though, which is that of these 47 technologies, they initially grow at a fast rate, and then they get on this essentially exponential growth, and then out here, they start to flatten out. This is a transformation that takes the S-curve and turns it into a line, okay? So, but then once they get up here, it seems like all of them fit, but down here, some fit and some don't. Now, it turns out this is not the only process you can write down. Another process well, I don't think that's the answer. Yeah. Oh, maybe batteries. Okay. So, so that's not the only process you can write down. There's something else called the Gompertz process that we'll see in a minute. What? Say what? Okay, great. Yeah, it's up here. Sorry about that. So here's the Gompertz process. This turns out to be the process that tumor growth follows. Now, why technology growth would look like tumor growth, I don't know. It involves the possibility that something can die. Instead of having a clear birth-death process, the bacterium's young, it lives for 3 days and then it dies. It's equally likely to die as it goes along. If you have that, then you get a process that looks like this. And in this case, you can see there's no kinks anymore. Everything sits on the same curve, though it gets noisy up in here. We're a little worried that this is partly data problems. We don't think these wild swings are real. We now actually have 190 technologies. A lot of the data is very bad. We're trying to figure out what's bad data, and we don't want to cheat. So we have to be careful that we're not like just fishing out the ones that lie on the curve the way we want them to. So you have to be very careful with this kind of thing. But it's very interesting that it looks like Gompertz is the best model. So that's giving us a clue about what that underlying process of technology growth is. But now back to my question, it suggests it's both. Insofar as we're staying close to this line, it's a deterministic process that we can use to predict. But insofar as it's different, it says there's noise. So there are these things happening that knock it off the curve. Donald Trump gets elected, that's bad for renewable energy, right? So, okay, oh good, that was nice. Now, but you can ask, the hard part about this is predicting where the asymptote is. But if you have an idea what your prior is, you can then ask, how long will it take to get there? So here we ask, how long does it take to get 80% of the way to the asymptotic value where the S-curve flattens out? Now, we took 80% because, of course, it takes an infinite amount of time by definition to get to the asymptotic value. But to get to 80%, this vertical line would be solar energy producing as much electricity as the entire current global electricity system. So it gets there in 2038 on average. These error bars show the accuracy of our prediction. I want to emphasize this is still work in progress. These error bars may widen in a future rendition, but part of what this is telling you is that that we can expect that solar energy is going to be playing a major role in the power sector within 13 years. In fact, this would be taking over the powers, almost taking over. This is capacity, not actual production, but that would shift it over to maybe 2039 or 2040. Okay. Now, this is what happens. We have tackled all those problems I made the list of that make this hard. We've put in effects to deal with all of those. We're also using a Bayesian estimation method, which is a much better way to do it because we end up not just with some parameters that we fit to the curve, we end up with a distribution, actually a conditional, a joint distribution for all of the parameters that allows us to understand what's the real uncertainty in fitting that data. And so this is a projection without assuming anything about the asymptotic rate for solar energy. Now this would be the entire electricity system. So in this forecast, it looks like we're likely to hit it in about 2042. This is also using the Gompertz model. The previous one was with logistic because it's a bit of an old plot. These bands illustrate the accuracy of the forecast. That is, each one of these bands is 5%. So this is the median, but this is the error bars that we expect to have in the forecast. Again, those error bars may need to be widened out a little bit before we publish this, but I don't think it's going to change dramatically. Okay, so that's my prognosis. Let me say one more thing about this, which is, suppose you want to ask, well, what about fossil fuels? What is the prognosis for them? You read in the paper all the time, oh, nothing's happening, fossil fuel production is not dropping, blah, blah, blah. But bear in mind, this is an exponential curve. And so because it's exponential, it means that it's still, solar energy is about 1% of total energy or less. But because it's growing exponentially and it's growing at 30% per year, that we can expect that within 5 years, it's going to take a major bite out of fossil fuels. It's just you really have to think in exponential terms, and you can't look at fossil fuels because it's like looking for a star when you're staring at the sun. Okay. Now, come on. Once again. All right. Maybe if I put it behind my back like that. I don't know. Well, okay. I'm showing this plot again, just to remind you about the costs. We've now done deployment. Let's now think about costs. And how reliable is it? I mean, you can see right here that if you just drew a line through this, you'd get a pretty good forecast going forward. But is that typical? I mean, maybe that's really special to solar energy? Well, just so you know, it's not too special. There's a very famous law that's been remarkably accurate that appears, we talk about all the time, Moore's Law. So, you know, what happened with Moore's Law? Gordon Moore, who was an executive running, well, he later ran Intel, I think, or I'm forgetting, Fairchild, I get the companies mixed up. He just plotted transistor density in integrated circuits over 15 or 20-year period. He noted it was an exponential. He initially said that, oh, looks like transistor density doubles every 18 months, and then he later adjusted it every 2 years. And the adjusted figure has pretty much nailed where we are right now, 70 years later. He did this in 1965. So remarkably good forecast. If you're a forecaster, that's the kind of, okay. I want to say that, okay, this isn't, just to show that I have a little bit of cred here. This is a paper we published in Nature in 2010. We forecast that the cost of coal-fired electricity, that solar would be cheaper than coal-fired electricity by 2020. And just to illustrate that this was not the standard point of view, in 2014, The Economist was still saying solar power is by far the most expensive way to reduce carbon emissions. So we were right. We pretty much nailed it. If anything, we were a little too pessimistic. But this was our forecast in 2010. And how did I make this forecast? Let me just, come on. Well, it doesn't matter. Made it by simply drawing a line through the data on log scale. So it wasn't like I was doing something brilliant. The amazing thing was that nobody at the IEA, none of the integrated assessment modelers had the idea to just plot the data on log scale and draw a line through it. So the question is, oh shit, we must be on a Windows machine. Okay, because what you're supposed to see is a fan here showing the forecasting accuracy. This is a forecast we made in 2016. And so we have those same kind of bands fanning out around this, showing the accuracy of our forecast. Because when I made that forecast in 2010, we couldn't, how could we convince somebody? Make a forecast, so what? You can look back and say, oh, this person was right. But really, to do a forecast, you need to say how good the forecast is. And if you can't say how good the forecast is, it's not very useful. So we worked quite hard. We gathered data on 50 technologies, and we came up with a way to make error bars by just effectively writing down Moore's law as a stochastic process with a noise parameter that we could fit to the data and then use to make a forecast. And we showed that on the 50 technologies that we had, by making out-of-sample forecasts, pretending to be in the past, forecasting the future relative to that point where we weren't seeing any future data, that the forecast, first of all, Moore's law was tied with something else called Wright's law for the best. I might come back and say something about that. And furthermore, our error estimates were correct. Don't know what's going on. Okay, it just moved. All right. So, this says what we did. We built a probabilistic model. We made 6,000 forecasts to test it, and we applied it to 3 scenarios in a subsequent project to 3 different scenarios. Because the question there was, what will the energy transition cost us? I mean, because you hear climate change, it's going to be expensive to deal with it. It's a burden. Who's going to pay for it, et cetera, et cetera, et cetera. I don't know what. Oh, yeah. Oh, can I do it by just doing that? Okay, good. All right. So this is just to illustrate that the forecasting method, actually it's a slightly different one that goes off of production, but it gives essentially the same results. Just forecasting based on the history. These are the 95% confidence intervals for the forecast here. And you can say that our forecasts have stayed well within those intervals for solar, wind, batteries, and P2X electrolyzers. It's a little harder to tell because the data is poorer, the time series is short and quite noisy. But it still looks reasonably promising. So what we did, wait, I don't want that. What do I do to advance the slide? Okay, I guess I can go to next and hit the menu there. What? Okay, so I just tap it on the left side. Okay, so what we showed in this study, where we constructed a scenario, we constructed 3 scenarios by hand, a fast scenario that just extrapolates the exponential rate we're on and levels it off at a reasonable point. This is before we had the S-curve forecasting stuff I showed you earlier. And we had a slower transition and then a no transition. And we measured everything relative to the no transition. And we showed that the fast transition is likely cheaper at any reasonable discount rate. In fact, we showed that the expected savings is $12 trillion in net present value. So substantial savings. We didn't optimize anything. And we tried to be highly conservative because we wanted to defend against any skeptic who said we were fudging the numbers. So whenever there was a choice, we made the pessimistic choice for renewables. And I just want to emphasize this doesn't we made a stochastic forecast, but there may be bumps in this road. But what this means is that even if we didn't have climate change, we should be moving to renewables simply because it's going to be cheaper. And this took into account grid costs, which are substantial. It took into account the costs of coming up with long-term storage with, we assumed, hydrogen-based fuels, storing enough fuel to power the whole globe for a month. So we assumed all these things. And if we didn't have that taking up a lot of expense, it would have been way cheaper still. And why is it cheaper? Because even though the cost for the grid goes up by a large factor, I forget the numbers, but maybe from spending 300 billion a year to 700 billion a year on grid costs, solar energy in particular gets so cheap that the sooner we deploy it, the quicker the cost goes down and the more money we save. Right, nuclear, well, I already showed you it hasn't gone down. It's actually 35 trillion more expensive than business as usual to have a scenario that's really heavily dependent on nuclear. It's also tends to go slow because it's hard to put nuclear plants into practice. And I also don't think small modular reactors are going to solve the problem. There are, of course, roadblocks. We really need to focus on energy storage. We need to expand the grid dramatically. Fossil fuel politics play a very big role. People complain about land use, although actually, when you look at land use, I don't think it's really a problem. And I mean, one fact is that we can generate all the amount of electricity that hits, amount of solar energy that hits the Earth is 10,000 times as much as we need to power the energy system. And, I come from New Mexico in the United States, a 100 kilometer by 100 kilometer chunk of New Mexico where there's virtually nothing right now, can power the whole United States. So, okay. There's also a lot of other advantages: cheaper energy, low volatility of energy prices, energy security, low pollution, lower environmental impact, more sustainability, and of course, the big ones, no greenhouse gas emissions. I think nonetheless, we still need better guidance. We need to figure out how to get storage up and running as fast as we can. We need to think about what are the best policies to make this happen. How can we do this and have everybody make a good profit? If we can see better into the future, we can avoid bumpy transitions where things happen that surprise us, and we can avoid stranding assets and wasting money. So now, let me close by saying, I'm going to now show you how we've incorporated these cost models for technologies into an agent-based model of the energy system. In this model, the agents are real energy and power firms. By real, I mean, you can see, our goal is to simulate every energy generation company in the world. So there's about 30,000 of them. Most of them are pretty small, but we simulate their decisions about, we simulate how they predict the future costs of technologies. Every year we decide, each company decides how much it's going to invest. It then decides what it's going to invest in. If it's a utility company, does it build a solar farm or does it build another gas-fired turbine plant? We then simulate electricity markets. So it's, standard, here we're plugging into a standard technology. We find the prices and quantities that each firm supplies, and we estimate their profits, well, their revenues, we know their costs, we get their profits, and we do it year by year. We loop around this. And let me just say, all of this depends on policies. We have to lay out a policy for each country, a time series of policies actually for each country, in order to factor into the decisions that get made. But it means that going forward, we can look at hypothetical policies to see what happens if we use this policy or that policy. So this is just a diagram of how the model works. Again, we have an energy market, we have an investment module, we model creations and exits of firms, we update the cost of technologies, and we go around the loop. And now I'm going to show a couple of movies, if I can get this to work correctly. So this is, first of all, the historical evolution for Canada from 1970. You see the date changing up there. These little blue things are hydroelectric plants. That's a coal plant. This is a gas-fired plant here. These are solar energy installations. The size is proportional to capacity. So we can see how the energy system got populated historically leading up to 2020. Now, we can then go to the next slide. Now I need to advance to the next slide. Come on. Yeah, can you get me to the next slide? Oh, okay. No, we went through one. Can you go back a slide? No, now we're going forward again. We're going forward. Need to go backwards. Backwards. One more backward. Okay, good. Now, here's a statistical model we built. And I have to say, we've got the model running. Why am I showing you Canada? Because a Canadian foundation paid us to do Canada first. So we're using Canada as a kind of test bed to get this whole procedure working well. And this is a statistical model where we look at the patterns, because we have 30 years of data where we have a pretty good record, more than 90% of the plants, essentially all of the firms, and we can see what happened every year as we went along, as you saw for Canada in this. We have that for the whole globe. This is a statistical model. Okay, and so you can see in this case, it actually installs a lot of wind. But this is what happens if you go forward to 2030. Okay. Okay, here we got this one. So here's a different model. Okay. In this case, what we have, the firms make decisions by estimating the return on the investments, by forecasting the costs, and you can see it now puts a lot of solar energy. Why? Because solar energy is cheap. Okay, so just to finish off, no, I need to get it. Okay, so let me just say, I think I may have said this already. We try to predict what's actually going to happen. So we're not just making projections, we're making forecasts. We try to make testable predictions so we know if they're wrong, and we try to test everything out of sample before we use it in real life, and we try to understand how good the predictions are. And this is the sort of architecture we're working towards, where I've showed you what our energy system model is going to look like. We have models for technological change. I showed you a simple model based just on historical time series. We also know a lot about the patterns in patenting that signal which technologies are going to make rapid progress. We've thought a lot about the types of policies that do a good job. We still haven't really done much of anything with agriculture. We've thought a lot about how the production network works, how household consumption works, and a little less about the financial sector, although I have a lot of expertise in that domain. And I think that's our last slide. Oh, there's my book, in case anybody wants to buy my book and learn out more about this stuff. So that's it. Thank you very much. How are we going to do it? Should we do and then do questions at the end?
No, let's do questions.
Do questions first?
Yeah.
Okay. Questions? Can't imagine no one has questions. Yes.
Thank you very much for coming to us. I used to study your work since my graduate school when you were dealing with complexity theory in Santa Fe Institute. And I'm really happy to have you here. My name is Merjanis. I'm professor of finance in Abu Dhabi University. And I would like to thank you for your presentation. However, very briefly, I have a couple of comments. First of all, you don't seem to have any explanatory factors in your analysis. And I do understand your modeling methodology, which really does not explicitly consider those. However, when one looks at the long term, one needs to have some suggestions about policy. And the lack of important explanatory factors such as geopolitics, such as changes in climate change is not explicitly modeled. Don't you think that that might be a little bit of problem when you decide to make a policy prescription? This is the first. The second is that at some point you mentioned that indeed, I mean, even if it were not for climate change, nevertheless, we should see investment in solar energy. I agree. But this is an endogenous loop here. We do have the investment exactly because we have climate change. And unless we take into consideration endogeneity factors, I think prediction might be a little bit problematic in this respect, unless we correct for this. And let me give you one more example, and I stop here in respect of time. You made your predictions, but let's see now what's happening. 5 years ago, 3 years ago, we did not have that much talk about artificial intelligence, and the talk was mainly academic. Now we have very, very real consideration of AI issues. And recently we see the news that coming from America, but not only in the rest of the world, that Google is planning to buy a nuclear factory or even establish one to be able to deal with the tremendous prospective needs of electricity for running the data centers. And we see this. This to me means that solar power may not be able to deal with it. It seems to me that we're coming back to nuclear power very, very forcefully. How would you model this? It seems to me the way that you are approach the long-term prediction does not take some important consideration that have arisen in the meantime into consideration. What is your view on this?
Yeah.
Thank you.
Yeah, so those are good points. Let me make sure I can go through all of them. So the first one is we're not looking at causal factors. That's true with the time series models that I showed you. That's not true with the agent-based model that I showed you. The predictions of that model are going to be highly policy dependent. And so it makes it possible to look at scenarios. It also makes it possible to think about geopolitics because at least, and let me just say, at the high level, in that model, we have to have a model of cost improvement. We don't have to have a model of deployment. That emerges endogenously from that model because each firm is making a decision about return on investment. And so that prediction emerges from that model. And so we do have at least a part of the cause happening there. I began when I was talking about deployment by saying there's two basic theories, right? There's one theory that there's an underlying deterministic process as there is for bacteria, though even that has fluctuations. Every Petri dish is a little bit different. Similarly, all the issues you say will affect whether we stay exactly on the curve or we go up and down. And also these methods are not about predicting exactly what's going to happen next year. They're about what's going to happen in the long run due to trends. And we see significant bumps when we look at those trends. What we do see is looking at 50 technologies or more, that these patterns are quite persistent, that it's rare that you ever see a technology break away from its trend in a dramatic way. I mean, you see some break with solar energy, but then it actually reverts back to the trend. And it is going to give us insight about politics because when we're simulating the whole world, then you're going to be able to see who the winners and losers are going to be and combine that with economic models that we're building. And I think we'll see quite a lot about that. Now, one of the main things we've seen, by the way, is that these long-term trends are really driven by the technology themselves. That's the deterministic part. As I showed you in the plot I made, that each technology establishes a pattern and it sticks to that pattern remarkably persistently, and the pattern is dramatically different between fossil fuels, or anything you mine out of the ground, which hasn't changed in 140 years, despite some bumps, or nuclear power, which there are no examples of nuclear power going down significantly, to solar energy that's dropped by a factor of 10,000. So admittedly, these predictions are not going to be perfect because there's a noise component that we don't claim to be able to predict. Hopefully I at least addressed all your points, even if you still don't agree with me. Sure.
The cost side from the demand side.
Wait, sorry, I couldn't hear what you said.
You seem to separate the cost side from the demand side as drivers of change. What I'm thinking is, don't you think that it might be a more fruitful approach if we compare an agent-based modeling approach with a stock flow consistent approach and with a machine learning approach and see what the predictions are saying, and based on, because these are sharing some similarities in this respect, and yet they would produce some different approaches. Well, what is your view on this?
Well, of course, one should compare approaches, but we have a stock flow consistent agent-based model for the macroeconomy. I'm not talking about this here. I talked about it yesterday, but we can use that model. We can take the energy scenarios that we're making here, and we can then feed those in to our macro model. Our goal is to be able to do that within a few months, actually. But we're looking at how the energy transition drives the economy. It's not the economy driving the energy transition. Within the energy agent-based model, though, again, we're not, in that model, the deployment is an outcome of the model, not an input to the model, okay? So we will see from that model whether we get something that matches what we saw from just looking at the time series. The reason with the time series model we're not putting both together is because of lack of data. To distinguish Wright's law and Moore's law, I haven't really discussed Wright's law, but to distinguish those, you really need cases where technologies reach maturity and where you can see the cost curve across the whole span. We don't have enough of those. We're trying to get more of them to be able to make a better model. There's an identification problem when you try and do that, because if you look at the virtuous cycle you would expect to see, which is that costs go down, so demand goes up, which drives up production, which causes costs to go down. When you try and make that model, it's very hard to distinguish. In fact, it's impossible to distinguish because of a fundamental identification problem. The demand exponent and the cost decline exponent, unless you fall off of the exponential curve. But if the data is on exponential curves, which most of the data is, we can't make that distinction. Hence, we're doing them separately so far. Because we have a lot of data on deployment alone, and we don't have the matching cost data for that.
Thank you, Professor.
So, anyway,
we do have a question online.
Yeah, okay.
Mariam, would you like to unmute yourself? Please go ahead and ask.
Sorry, do you hear me?
Yes.
Thank you so much, dear Professor, for your nice presentation. I'm Mariam. I'm a Berlin University Alliance in Charité, and I have a quick question about the assumption of your model. Since you told you applied a logistic linear model, but I saw that your assumption is a bit different from the pre-assumption for the linear model, logistic linear model, about the noise and also heterogeneity in the noise and autocorrelation between the noise. And it was a bit challenging for me, and I didn't understand how you use this model with the pre-assumptions. Thank you so much.
Okay, so I think the question was, I sort of teased you by saying, these are the effects that you need to deal with. I didn't really tell you how I dealt with all those effects, I guess because that gets kind of technical, and I didn't think this was a technical audience, but it'll all be there in the paper when we have it. But basically, we found a functional form, because it's a reduced form model. I mean, we found a functional form that accommodates those things. We spent a lot of time studying what do we have to do to get the noise to not be heteroscedastic, and so on. So I'm sorry, I don't really want to go through the technical details because that'd take 5 or 10 minutes, I think.
No, we do have another question that I'll ask you, and then we can go back to the audience. How do we factor stochasticity in our agent-based models, for example, earthquakes and its impact on energy market?
Well, so to first approximation, we don't, right? I mean, if somebody could give us a prediction of an earthquake, we could factor that in. If you heard my other talk yesterday, we talked about modeling COVID, where we did anticipate the size of the shock from COVID. How do we do that? We did it by looking at who would and would not be able to go to work, what would happen to the demand and the industries that COVID would affect. And we built a model that allowed us to see when industries would run out of essential materials to manufacture. We made an extremely accurate forecast in that case, and we made it in real time. But future earthquakes and disasters, it's, we can put in hypothetical disasters and see how big an impact they would cause. So we can do that, but we can't really predict what those things will be.
Thank you. Let's take one last question before we move to the second session.
Thank you. Thank you very much for this really enlightening presentation. I enjoyed it. I think I learned a lot, and I'm looking forward to reading the papers that come with it. I'm an economist. I'm a professor at New York University here in Abu Dhabi, and I've worked in mostly in macroeconomics and machine learning, so kind of for the background. What I'm curious about is you presented several forecasts, right? So some of the forecasts went up to 2070, others went to 2030. So I assume that you just have different papers and different horizons that you showed us here. Because
yeah,
Mike, okay, good. So I think as an economist, right, we always think we are the center of the universe. And so let me ask you, based on the macrocosm and the many sectors or players that you kind of illustrated here in the agent-based model, can you give us an idea about how these sectors interact, and in your model, what are the major drivers, right? How important is this sector? How important is that component of the model? So that we kind of try to understand what we need to focus on.
Yeah.
Thank you.
Yeah. So first of all, on the time scale, that's just a matter of, I told my colleague, hey, generate some plots for me. He chose 2030. So out to 2070, I start to get pretty skeptical about forecasts in general. But I think we can make some forecasts up to 2050 or so. And I just realized somehow I missed a slide, but okay, that's all right. Now, on the question about how the sectors interact, so we're taking things one step at a time. We're starting just with the energy generation sector. So how do we actually make the energy? And so we're modeling all the firms in that sector, all of their decisions. But of course, you have to have some model for demand. So to start with, we take demand to be exogenous. We assume it keeps going up at 2% per year as it has. But then you can start to ask, well, wait a minute, what about electricity versus liquid fuels? Well, we know electricity is going to get bigger and bigger, and it's going to get bigger faster than 2%. But to really model that, then we can model the downstream sectors. We can do the same thing for the electric vehicle versus ICE vehicle business. We can also go upstream back to, well, we're already going to do oil mining. We're doing oil and gas mining in the next wave of this. But you can look at minerals and mining, and you can basically explore the supply chain going up and down, and try and get a more and more coherent picture. And then on top of that, you can lay a macro model that now tells you about consumer behavior. And so we've again built a very empirically focused model where we, have heterogeneous households who can look at what are the consumption patterns of wealthy households versus poor households, et cetera, and lay that on top of the energy model to see how it's going to affect things relative to some baseline. Now, I'm nervous about making an unconditional macro forecast. That's extremely difficult problem. But at least I think we can forecast, say something about how the energy transition will affect the rest of the economy. And actually, in particular, we can also do labor, which I think there are the answers, are answers I think are fairly reliable for how the labor force will respond and how we have to adapt the labor force to accommodate. I had some slides on that actually, but.
Thank you very much.
Thank you. Thank you, Dr. Farmer, and thank you for joining us. in Abu Dhabi, and we look forward to seeing you more here in Abu Dhabi. Our next speaker is Professor Mao, Professor of Practice at Khalifa University, who will be presenting his case study on market entry of emerging clean technologies. Please welcome on stage Professor Mao. Thank you.
Okay, thank you. And we have seen the great predictions of Professor Farmer. And let's see first, what is the current status of investment in energy transition? My first slide here. Yes, here. This is the one. Yeah, my first slide. Oh, oops, it's gone. This is the plot data. Okay. Yes, this is one just announced, released a week ago by Bloomberg to show that the state of global investment in energy transition. And for the first time, that the global investment in energy transition exceeded $2 trillion for the first time. And that's up about 11% on the previous years. And the largest sectors are the renewable energy, electrified transportation, mostly EV, renewable energy, and power grid. I put note here that although it's relatively small, the investment in energy storage accelerates very strong, 36% last year. And in contrast, investment in clean hydrogen, carbon capture, storage, there's a reduction. And the first message, very simple message I want to pass to everyone is transition to clean energy will and is continuing to grow. I think that consistent with what Professor Farmer's prediction. Next one. The four so-called mature sectors. What are mature? Means the technologies are proven, commercially scalable, and business models are very well established. Those four mature sectors, renewable energy, storage, EVs, and power grids, they represent the largest, 93% of total investment. And another number important here is they have about 15% of year-on-year growth, considering the problems in economy, global economy over the past few years. It's really pretty good, healthy growth. Next one. The second simple message I want to pass is successful transition to clean energy must be and is a profitable one, as Professor Farmer actually predicted many years ago. I noticed that. And energy transition, as you read here, will only succeed if clean energy investment generates returns and meet the requirement of companies and investors. And this plot shows the KPMG. They did a survey of 1,400 global energy transition investors globally. And the financial investors, they are looking at the top reasons why they're investing in energy transition assets is financial returns, followed by portfolio diversification, and also regulatory compliance, risk management, and technical development are equally important. So these are major reasons. So financial returns is the most important. That's really behind the drive of why we are seeing growing investment and the growth, big growth of rapid growth of the clean energy. The drives I put here is the pace of technology progress has been very remarkable in the past 5 years. Costs are steadily decreasing, supply chains is strengthening. And today we probably see that the oversupply from China, but I think the supply chain will be more stable in the next 2-3 years. I'll put another note here is related to what the question about the Trump just geopolitical. The technology advancement made over the past decades, not only years, decades, are now delivering results. We see that. So the momentum is difficult to slow down. I use a nice language. And the geopolitical shift will have only limited impact. Yes, we may see reduced funding for certain areas, reduced government loans in the US, for example, but the overall picture is very clear. It's growing. Next one. So I grew up in the technology base and look at the startups. So what are the challenges? What are important for energy startups? Very simple, demonstration of technology's long-term reliability and performance metrics like efficiency, durability, and operational cost, etc. So this plot coming from IEA a few months ago, before this year. The important note here is that energy has outperformed other VC segments. That's a very important message here. Since 2021, for early stage, we talk about early stage equity funding of startups. I look at more of early stage technologies rather than looking at prediction. That's Professor Farmer's job. And since 2019, corporations start to put their own money to invest technologies, which implies they're making money. And they want to stay ahead of the curve, so they develop competitive advantage in rapidly evolving technology landscape. And corporate R&Ds now has been rising to invest in hard to decarbonize difficult sectors. Next one. The third message is transition to clean energy may feel hard at times. I noticed there's one similar statement from Professor Farmer's presentation. I won't elaborate, but very simple. Easier opportunities have been taken. Like early renewables developers have got the best site with cheapest grid connection and so on. So maybe for some of the developers or investors think that it may be difficult to enter. That's wrong. So the next phase of transition, in particular, for 2025, for this year in particular, I look at the different organizations, their predictions in the past 2 months, only in the past 2 months, from Bloomberg, SP Global, Deloitte, and KPMG. They summarize what they predict 2025 and within the next 2 to 3 years, short term. For example, Bloomberg emphasized that energy storage would continue to grow, getting charging infrastructure, the driving demand clean energy to aviation, shipping, heavy industry, that is a bit more difficult to decarbonize the sectors. SP Global, they said AI-driven climate tech, clean energy solution for data center. When AI industry goes up, they need more data centers, non-duration storage, and so on. The different, there's some differences, but next one. One common thing is a highlight here. All these predictions and also other organizations, they emphasize energy storage. They'll be having a large percentage, large growth, already having, and we're in the next 2-3 years continue. So happen to be myself has been working in the storage sector for the past, I think, for 15 years. And that's why I'm going to use a few simple examples as a case study to show you how to really find the entry point to the market. Next one. Battery energy storage, there are supporting 3 sectors. One is fueling in mobility, basically electric vehicles, energizing grid power grid transformation, and we do need energy storage technologies to enable larger percentage of the integration of renewable energy to the power grid. That's a technology issue. And also making 24 around cloud renewable power a reality. This is not talking about the power grid, it's about different industry applications. These 3 enablers for these 3 sectors. Next one. So we developed technology more than 10 years ago that we developed a battery technology. This is called lithium titanate-based technologies. I think we were able to make the best materials and making the batteries. This is the properties of these materials, these batteries. It will never explode, will never catch fire. This is one of the very good benefit. Best in the line. Operation temperature, -30 to 60 degrees C. No need of any protection or heating. Operating temperature, 20 to 30,000 cycles, which is several times, 5-6 times better than existing ones. The charging, 10 minutes charging, very fast. Everyone likes it. But there's one effect or shortcoming. That is so-called energy density is about half of what has been in the market, which means this battery, because this property is low, it's not feasible for passenger cars. This is largest growing sector. So where to find the entry point to the market? Next one. We look at a market which is very difficult to decarbonize. and there was no solution when we entered this market. And this is the heavy-duty trucks, very heavy-duty. How heavy? 100 ton is typical ballpark number, starting number. Low fuel efficiency, high maintenance costs, toxic emissions, and so on. Next one. So we made design. So how to really change the curve? Change curve means the status is to implement renewable clean technology to that particular sector. So we designed a hybrid electric system, the battery system plus a small diesel engine. For example, for the startup car, our design was battery providing power, engine not working, uphill, because for mining in particular, we need big power, so the battery not enough. We have the small engine working also. Engine not working when downhill, battery charged by the braking, we were able to recover more than 95% of the energy. And flat road, engine providing power and charging battery if needed. I won't go into detail. Basically, we make the 9 and 100 ton design. And the final solution is we're able to save the fuel cost of 50 to 70%, depending on the status of the working conditions. And remember, for mining field in particular, if you're familiar with that, that is more than 70% of operation costs coming from fuel. If we're able to save 70% of the fuel, which means we're able to save 50% of the operation cost. That's why investors have interest. Go down, next one. So we made the CAD modeling before we built these the big truck in collaboration with truck company. Myself is not building trucks, where we are the battery company, fund the company. Next one. This is manufacturing. We receive VC funding, building factory, making battery system. Next one. I just go over these things. And after actually less than 2 years, the very first hybrid electric heavy duty truck was made. And we debuted, we announced that at the international show. So the timeline is, this is something which I did before I came here, almost 10 years ago, that we found the company. We startup Series A, $7 million, making batteries in collaboration with one of the leading truck companies. And the end of 2016, we announced this truck. We showed the truck at the international exhibition. And then almost 1 year later, my battery company acquired 90% of the equity of the truck company. I suddenly become a truck company chairman. And then 1 year later, I sold the company to the multi-billion-dollar enterprise. Then free, and then I can come here. Next one. And then after this one is there was news, international news. We are the first in the market. One of the reporters said that yes, this is a big one. Everything's good. They report all these things. At the time, I was still at Berkeley, and they said we're to have a self-driven future. AI was just started at the time, not like today. And by this is 2022, in collaboration with my colleagues at KIT, Karlsruhe Institute of Technology in Germany, we developed technology. And my colleagues, not myself, and they are taking lead of negotiating with investors to implement AI technology to this type of heavy-duty vehicles, not only vehicles, but also the whole working side. The vision would be in the next 5 years or so would be the first unmanned, say, mining side or construction side. So this is just one example to show you that although you have something, technology, which does not appear to be useful, but in reality, if you look carefully, you should be able to find entry point because the market is so big. Next one. The second example is what we are doing right now at Halifax University. And that is the same battery technology, look at the applications in grid and power grid transformation, make the market of energy storage. The problem is fire safety. There's so many fire incidents. If you have to pay attention to it, lifespan of batteries is not enough. Solars can have 20 years, even 25 years, but for battery, no more than 3 or 4 years. Temperature range for the colder region, you need to have the heating element on those things, and also charging speed, which we also want to be fast. Next one. So this is an example just a few weeks ago. So I was able, before coming here, I just check, and something happened this year. The world's largest battery plant on fire in Central California, unfortunately. So they are using the batteries which can catch fire, and as you see, catching fire. Next one. For our system, we are building, again, in collaboration with a reputable company, a startup company. We build a system integrating battery energy storage unit, PV power generation, power conversion system, and energy management system to form a microgrid. Essentially, we're building the desk scale, the cabinet scale, the microgrid as a demonstration. And we use the highly reliable ADIA batteries, which, as mentioned, that it will never catch fire from fundamental physics and chemistry, and so on. So this one, and next one. This is the system that, again, just emphasize that I just mentioned that this battery system, although they have lower energy densities, but would never catch fire. Lifespan is, I mentioned this before, 20 to 30,000 cycles. Wide temperature range, -30 to 60 degrees C. Here, 60 degrees C is not enough. At 70 degrees C will be better. Fast charging and the low maintenance cost. So this is a very simple comparison. The cost of this battery, if you buy individual battery, is about twice of the price of the whatever in the market, and like Tesla using. The lifespan, 8 years. For them, only 2 years. For long-term investment, for the energy storage, usually it's long-term. So say for 8 years, for example, per 1 hour, we need 2 AED. For long-term, we need 4 cycles, will be more expensive. From long-term point of view, that although individually expensive, but because of long lifetime and other benefit, we think that these would have a market. Next one. And the third case study is we try to think that the company combining energy storage, what we have, with solar energy to enable the water generation from air, 24 hours. So during at night, there's no sun. So how would the solar energy power the operation? So basically, the batteries during daylight, 8 hours, the solar power the water generation. Also, the charge the batteries. When sundown and at night, the batteries would provide power for this operation. So we have next slide. We built the entire system, which has been running for a little over 1 year on the KU campus and Halifax University campus, and we are making a business case. Again, looks like it's expensive, but we are able to make a business case. It's right now actually under review by our sponsor, and we're able to have a case that with IRR more than 30%. This is something which, again, I'm waiting for my sponsor's conclusion decision. Next one. So this is a summary of giving you 3 simple examples, all related to energy storage, to show you that there are opportunities, and but we need to find the right entry point to similarly more expensive, difficult to enter in the market to enter. Next one. And the final slide is mentioned. I'm the director of the Aspiris Institute for Sustainable Energy, for which at Halifax University we look at power generation, grid-scale energy storage, renewable energy integration, smart transmission, distribution, demand-side energy efficiency, in particular, the more efficient integration renewable power to, for example, desalination, the better EV charging, and building energy efficiencies. And now we have a small team doing the sustainable energy policy techno-economics. And thank you for your attention.
Thank you, Professor Mao. Do we have any questions?
Thank you, Professor Mao. my colleague at Khalifa. I'm George Zuberi from Mathematics Department at Khalifa University as well.
Yes.
So I enjoyed your talk very much, and I was wondering concerning the quantitative models, for example, you talked a lot about entry points and when you decide to invest, do you make use of any, let's say, quantitative techniques such as operational research or real options or things like that, or is it mostly based on economic indicators and gut feeling?
It's a very good question. When I was a student at Berkeley, which I was an engineering student, but also I went to business school, we did study the different cases and predictive models, including the quantitative models. Not very much, but we do have. But for the examples there, I'm going more toward the market, not particularly using any specific models, because yeah, I think one of the class at the business school is the market is everything. It's quoted the exaggeration, but we go to market to talk to investors, talk to the end users, what their problems. I just go that a slightly different approach to decide what would be the best entry point.
I see. Okay. Yeah. Perhaps there's opportunity here for collaboration because sometimes
the model is useful. Yeah, actually, and hindsight that we studied the model, we know those things. So when we talk to investors, talk to the market player stakeholders, we know what to ask, what to, we know what to ask basically.
Thank you very much.
Thank you.
Thank you. We have another question over there.
Thank you very much, Professor Mao, for your interesting and practical information you share with us. I have two concerns that I would like to share with you. Take first the issue of electricity storage. I think this one, in order to conceptualize whether it is investable from an investment point of view, profitable, one needs to compare it with the possibility of import and export of electricity. Take, for example, the cost of storage versus the cost of importing electricity. And perhaps in countries like the UAE, then storage is maybe very important and from a national security perspective. But how about if there is some confederation in the GCC country and they can do import and export electricity? This is happening in Europe these days. This issue of the electricity is being, to a large extent, electricity shortage solved through some, well, I don't think it's very efficient, but it's moving towards there, some sort of a unifying electricity market where imports and exports will pick up the slack. This is one consideration that I think you need to make to board. And the second one is a technology one. Suppose that you are a firm and you are thinking about investing in these technologies, solar technologies or anything else. Suppose that you are a manufacturing firm, and I'm using your example. Why would you consider competing against Tesla in the US or against Geely and a few others in China? The sunk costs are huge. Maybe it would be more economically to jump into a new technology such as say, hydrogen. And that's exactly what we see BMW is doing. So I also think that you need to take this technology quantum leap, if I may say, into consideration when you make your business plan in these projects. Thank you.
Thank you for the 2 points. Just briefly that for the cost, we do look at the whole life cycle and every scenario. Like for the UAE, I don't mean that everything has to be in the UAE, but the UAE, we develop technology, we can start a company, and we have investors, and the technology and the manufacture, the product, not necessarily for UAE. UAE market relatively small. Go to a different market, which from investment point of view, where's the return? And for the technology-wise, that you notice that I look at we develop technologies, but we look at the differential market. We do not try to compete with, they said, Tesla. You said hydrogen. What about hydrogen? We do look at hydrogen. Before I came here, I had the 3 projects on hydrogen technologies, but I did not find any hydrogen companies because I cannot make the right balance sheet. Economically not feasible yet, although the cost still going down at a slower pace. Your point, 2 points are absolutely right. Thank you.
Thank you, Professor Mao. One more question.
Yeah, you quoted costs. I would think that you're operating at a much smaller scale, and that as you scale up, your costs would come down. And so
Yes.
maybe you're actually being pessimistic by not taking that into account. Or were you, I mean, when you quoted the cost, how did you figure the cost out? And it's going to change through time.
Two things. When I founded the company, I run my company, I have a real cost. The scale is not big enough.
Yeah.
Right? I have that profit margin, how much. But when I write business plan for the multi-billion-dollar to be interested in my company, and I think investors know that we have professor, which to assume that how large is the market? Assuming we have a 20% market, we are the first. How many batteries will be needed? What would be the cost in that scale? Yes, we look at the two cases. In my own operation, real operation is more expensive. But for investors who are willing to invest for the to scale up, yeah.
Thank you, Professor Mao, for your presentation. And thank you, Professor Doyne Farmer, for joining us today. For our online guests, thank you for listening in. And for our in-person guests, we have a networking session. Please join us and you can ask more questions. Thank you and have a good evening.